Alright, today we're going to learn how to predict the products of a single replacement reaction. So before we get started, let me just review that a single replacement reaction is going to happen when you have a single thing and you have a couple, and what you're trying to see is if that single thing will kick out something in the couple. So for example, maybe A and B could switch places so that B gets kicked out and A is in the couple. So we're going to learn how to, first of all, predict if that will happen, and then if it does happen, how to predict what to write on the other side of the arrow. There are just a few rules for this. We're going to use something called the activity series. And I'm getting ready to show you what that is, but it's in your reference packet. So if you have that reference packet, or if you could pause this and go grab it, it would definitely help you. So the rule is, basically the activity series is a list of elements ranked by how reactive they are. So closer to the top of the list are the more reactive elements, closer to the bottom are the less reactive ones. And the rule is that the element that is higher on the list gets to have the partner. And if it's hard for you to write and listen to me at the same time, maybe pause this and fill in your notes and then you can just listen. So again, the element that's higher on the list gets to have the partner. Well, sometimes it already has the partner, and that's when the reaction does not happen. So not every single reaction will produce something different. We're going to go through some examples in just a few minutes. You can go ahead and write those two examples down if you want, but we're going to go through several together. And then the last rule before I start to show you how to do this is that you don't ever want to bring a subscript from the left of the arrow to the right of the arrow. So for example, if A had a subscript right here, do not bring that 2 across the arrow. The only exception is if you have a polyatomic ion, like if you have sulfate in your compound, so you have something right here bonded to sulfate, you can bring that 4 if it's part of the sulfate. So hopefully at this point you can recognize those polyatomic ions. You can bring those subscripts, but not any of the other subscripts. Alright, let me show you how to do some of these. First of all, you want to find your activity series in your reference packet. And again, it looks like this. It's a list of elements. Towards the top are the more reactive and towards the bottom are less reactive. Notice that there's 2 lists, and that's because these are all negative ions, and if you have yours that you printed out, you might want to just make a note that those are the negative ones, and then all of these are the positive ones. Alright, let me show you the rules for this, and once you go through the steps a couple of times, I think you'll get the hang of how to do it. It's basically just a whole bunch of steps to follow. The first thing you want to do is go ahead and put oxidation numbers on all 3 of your things. So if it's single replacement, you're going to have 3 things, 1 by itself and then 2 in a couple. And if you have those oxidation numbers, it will help you figure out what's going to change with what. So silver you had to memorize is a +1 charge, zinc you had to memorize is +2, and chlorine you can look up on the periodic table is -1. Once you get your 3 charges, I want you to circle the 2 that have the same sign. It doesn't matter what number they are, but you're looking for either 2 positives or 2 negatives. Those are the 2 you're going to compare on the list. So let's go over to the list on the right, and you're going to check the positives. What you want to do is find silver and find zinc. So here's zinc, and here's silver. And the rule is that the thing that is higher on the list, like literally closer to the top of the page, that one gets to have the partner. So in this case, zinc is more reactive than silver, so zinc gets to have the partner. Well, it already has the partner. It's already with chlorine, and so this is a case where nothing will happen. And that actually saves you a lot of time because you don't have to do anything else. You just write DNR for does not react, and you can move on to the next one. Alright, for this next one, here are the charges. You had to memorize zinc and silver, and nitrate you can look on your list of polyatomic ions as a -1. We already compared these 2, so we know we're comparing the 2 positives, and they're the same ones as the last reaction, and we already said that zinc was higher on the list. So that means that zinc needs to have a partner. So now what you have to do is to rearrange this reaction so that zinc gets a partner. So the only thing that zinc would be attracted to is something that is the opposite charge of zinc. So don't put zinc and silver together because they're both positives. You're going to put zinc with the negative, and always write the positive one first when you do a compound. So we're going to put zinc first, and then nitrate. Whenever you write an ionic compound, don't forget to cross your charges. Zinc has a +2 charge, and nitrate is -1, so you need to bring that 2 down to nitrate. Plus, the thing that got kicked out of the compound. In this case, the thing that got kicked out was silver. The only thing you need to check when you write an element by itself is if it's one of the Hofbrinkel elements. So if it's one of these 7, you need to put a 2 on it when it's by itself, but otherwise you can just leave it alone. And then the very last step is to balance the reaction. So it looks like we have one of everything except nitrate. We have 2 of them on the right. It looks like we have 3 on the left, but remember this is actually just 1. If you don't have parentheses, it means you just have 1 of them. So what we need to do is to put a 2 in front of that silver to make it have 2 nitrates, but then we also changed silver, so we need a 2 right here as well. And then it should be balanced. And those are all the steps. So I'm just going to go through a few more of these for you so you can check and see if you're getting them right. All right, this next one, we can go ahead and put charges on K is +1. Actually, let me put it on the top. Phosphate you can look up as -3. And then we get to copper. And you're like, well, copper is a transition metal. How are we supposed to know what it is? This is where you have to do that X equation to figure out what the charge on copper has to be to make the whole compound 0. So we have 3 coppers. We don't know what the charge is. We have 2 phosphates. The number on the outside tells us how many. We know that it has to equal 0. And you can look up phosphate's charge as -3. So you should get 3x equals 6. So in this case, x equals 2. And that is the charge on copper. All right, so now we're ready to look at our elements. Again, we're going to compare 2 positives. So let's go over here and find those 2. We need to find K and Cu. So let's see. K is way up here, and copper is way down here. So K is higher than copper, which means K gets to have the partner. So this reaction will happen, and we need to rearrange it to give K a partner. Again, K is not going to be attracted to copper because they're both positive. So you want to put the opposite charges together. So the only thing it can stick to is PO4. Now notice that I brought that 4 with me. The 4 is part of the PO4. It's part of the polyatomic ion, but I did not bring the 2. The only reason that 2 is there is because it's bonded to copper, which has a +2 charge. Now that it's bonded to K, it actually doesn't need that 2 because K is +1 and phosphate is -3, so we do need to bring that 3 down to K. So don't bring subscripts across the arrow unless they're part of the polyatomic ion. Don't forget to cross those charges, which we just did. And then the last thing is that Cu got kicked out. The only thing you need to check on Cu is if you need a 2 on it. If you look at the Hofbrinkel elements at the top, Cu is not a Hofbrinkel element. It's not diatomic, so we don't need a 2. But we do need to balance this reaction. So let's see. I see 2 phosphates on the left and only 1 on the right, so we can put a 2 there. We need 6 Ks because 2 times 3 is 6. And we need 3 coppers, and that should balance the reaction. All right, let's look at this next one. Aluminum is +3. You can look at that on the periodic table. Chlorine is -1. Calcium is +2. So again, we're going to look at our 2 positives. They won't always be positive. It just happens to be positives in these. And we're going to find aluminum and calcium. Aluminum is right here. Calcium is right there. Calcium is higher on the list, so again, this reaction is going to react. So we need to give calcium a partner. The only thing that calcium is going to be attracted to is chlorine. So we're going to put calcium with chlorine because we need opposite charges. A couple of rules. Always write the positive one first in the compound, and don't forget to cross your charges. Calcium is +2 and chlorine is -1, so bring that 2 down. And then aluminum got kicked out. Aluminum is not diatomic, so we don't need a 2 on it. But we do need to balance the reaction. So chlorine's got a 2 and a 3 on either side, so we're going to have that 2-3 issue. So we're going to put a 3 here to make that 6 and a 2 here. And then we just need to fix calcium and aluminum. We can put a 2 there and a 3 here. And it should be balanced. So what I want you to do now is to pause this video, and I want you to try the last 3 by yourself and then play the video to see your answers. And I'm going to pause it and go ahead and write the answers to save time so you can check them when you're done. All right, check your answers, and let's see how you did on these. So in that first one, notice that we were comparing chlorine to iodine. So chlorine is up here, iodine is here. Chlorine is higher on the list than iodine, and that's why the reaction doesn't happen. Chlorine needs to have the partner, but it already has the partner. It's already with sodium. For the next one, same thing, we were comparing lithium to sodium on this one, so here are those 2. Notice that lithium is higher on the list than sodium. So lithium gets to have the partner, but it already has the partner. It's already with hydroxide, and so we don't need to do anything. It just doesn't react. All right, this last one, there were lots of places for mistakes. So be careful. If you didn't quite get this one right, just look at your mistake and make sure you don't make that mistake again. The first thing to recognize is that we're comparing bromine to iodine. So if we go back to our list up here, bromine is up here, iodine is right there. So notice that bromine is higher on the list, which means bromine gets to have the partner. Be sure you don't put bromine with iodine. Those are both negative. They don't like each other. You want to put bromine with a positive, but since you were just focusing on bromine, it's really tempting to do this. So be careful and make sure you always put the positive one first. We do need to cross charges, but notice it's +1, -1, so they cancel out. The next thing to notice is this little 2 right here. If you look up in your Hofbrinkel elements, iodine is one of the diatomic elements. So once it's by itself, once it gets kicked out, you do need to put that little 2 on iodine. It didn't have a 2 on the left because it was with sodium, and when it's bonded to something, it doesn't necessarily get the 2. But once it's by itself, that's where you have to put the 2 there. And then to balance it, we had to fix the iodine and the bromine with those red 2s, and then that fixes sodium in the process. So that's it for single replacement. There's a progress check for you to practice being able to do this. It's really helpful if you can go through these steps all by yourself and then check your answers. So make sure you wait to look at the answer key until you try them by yourself first. Good luck.